Hello, this is Math 10150 Lesson 5, Systems of Linear Equations with 3 variables. Last video we did 2 variables. This time we're going to do 3 variables. So, a system with 3 equations and 3 variables, and it's a linear system, will most generally look like this. We will have 3 equations with 3 variables. Our variables are x, y, z this time instead of just x and y. And we need 3 equations to get a single solution. Okay, and so in this system, x, y, and z are variables that we need to solve for, and a through L are just constants. So a solution to such a system is an ordered 3-tuple. So instead of an ordered pair, we have an ordered 3-tuple, x1, y1, z1. And in order for this 3-tuple to be a solution to our system of 3 equations, is that it must satisfy all the equations. So if you plug in the same value for the variables x, y, and z, it's going to work for all 3 of these equations. Now there are many different types of solutions that can happen. As we saw with a system of 2 equations, we had some paradoxical systems with infinite number of solutions or 0 number of solutions. And for the purposes of this class, the types of systems that we'll be working with 3 variables is that there's going to be one solution, one 3-tuple, that's going to be the solution of our system. And the methods with which we will solve is some sort of combination of substitution and elimination. So let's first see a simple example of such a system. So one example is we have to solve the following system: 4x plus 3y plus 2z equals 44. Second one is 3x plus 4y equals 36. And the third one, we have 3x equals 12. So what makes this system a bit simpler than your standard system is that the third equation only contains one variable and the second equation only contains 2 variables. So we're able to solve this by repeated substitution. So we start with the simplest equation, 3x equals 12, and we solve for x, and we have one of the solutions, not solutions, we have one of the one of the entries in the 3-tuple. And now we use that and plug it into the second equation. The second equation is 3 times x plus 4y equals 36. But now we know what x is. X is 4. So now we can solve for y. 12 plus 4y equals 36. 4y equals 24. And y equals 6. So now we have a second entry in our 3-tuple solution. And now we know x and y, we can plug it into the third equation, which is 4 times x plus 3 times y plus 2z equals 44, and we can solve for that. So x is y is 6, and x is 4. And now we can solve this equation for z. That is 16 plus 18 plus 2z equals 44. That is 34 plus 2z equals 44. 2z equals 10. Z equals 5. And that's the third and final entry in our 3-tuple. So the final solution to our problem is the 3-tuple 4, 6, 5. This is the final solution to our system. And this was an easier example of a system because, again, the third equation only had one variable, the second equation only had two variables. In our next problem, we're going to do something more difficult. We're going to solve the following system. We have 4x minus 3y plus 2z equals negative 29. Our second equation in the system is 6x plus 2y minus z equals negative 16. And our third equation in the system is negative 8x minus y plus 3z equals 23. And what I want to do is we're asked to solve this. We need to find a 3-tuple xyz that will satisfy all of them. Now there's many places where to start. One way is to use elimination to eliminate one variable and get an equation of just two variables and not three variables. That is what I want to do. I want to eliminate the variable z. So what I'm going to do is I'm going to take the first equation, 4x minus 3y plus 2z equals negative 29, and I'm going to add to it twice the second equation because I want to have 2z minus 2z. So I multiply the second equation by 2 and I get 12x plus 4y minus 2z equals negative 32. And now I can add these equations and I get precisely what I wanted. I'm eliminating the z variable. And so when I add these, what I get is 16x plus y equals negative 61. So this is my first equation with two variables. I cannot solve for x and y yet. I don't have enough information. But what I can do is I can create another equation with two variables, also x and y. So now I'm going to choose the second and third equation. And I can choose the first and the third, but I cannot choose the first and the second because I already did the first and the second. So what I'm going to do now, I want to eliminate the z variable from the second and third equation. So I'm going to write the third equation. I'm going to leave that as is. And I'm going to multiply the second equation by 3. And I'm going to get 18x plus 6y minus 3z equals negative 48. And the third equation stays the same. And I'm going to again be able to eliminate the z variable, and I'm going to get 10x plus 5y equals negative 25. And now I have a second equation, I'll call that v, a second equation in the variables of x and y. And now I'm going to solve this system of two linear equations and two unknowns. So this is my equation A, and this is my equation B, and now I'm going to solve this system. Solve this two variable system. Again, I can use any method of either elimination or substitution, but what I'm going to do is I'm going to multiply A, the first equation, by -5 because I want to eliminate. I'm going to multiply this by -5 because I want to eliminate the y variable. So equation A becomes -80x minus 5y equals 305. -5 times -61 is 305. The second equation I leave untouched. And now I add them, and I successfully eliminate the y variable, and I get -70 x equals 280, which means x must equal -4. So I got my first entry in the 3 tuple. And now I use any equation with x and y to figure out y. I'm going to use my first original equation, 16x plus y equals -61. So x is -4. This makes my equation -64 plus y equals -61. So y must equal 3. That's the second entry in my 3 tuple. And now I use any equation with x, y, and z to figure out the z. So let me use the first one. I have 4 times x minus 3 times y plus 2z equals -29. So x is -4 and y is 3. So this becomes -16 minus 9 plus 2z equals -29, which is -25 plus 2z equals -29, which is 2z equals -4, and z equals -2. So finally, I have all the elements of my 3 tuple. It's the solution to my problem. -4, 3, -2, and this is the final solution. So the goal, there's many different ways of doing this, but the general goal of solving a system with 3 equations and 3 unknowns is to eliminate one of the 3 variables and get just a plain good old system of 2 variables and 2 unknowns. Solve that in any method you know, and then start plugging in until you get all the 3 entries of the 3 tuple. Let's do another example. we're asked to solve the following system. X plus 6y plus 3z equals 4. 2x plus y plus 2z equals 3. And 3x minus 2y plus z equals 0. One thing that we should notice about the system is that the right-hand side of one of the equations is 0. This makes it a bit easier to work with. That means we can express z in terms of x and y. So we're going to convert this one and express z as 2y minus 3x. And now what this gives us is we can now plug in that value of z or substitute it in the first two equations. So what do those become? First one is x plus 6y plus 3 times z equals 4. And the second one is 2x plus y plus 2z equals 3. And now instead of z, we're going to put in 2y minus 3x. And now this becomes a system of two equations with two unknowns, and let us simplify that. So we're going to distribute the parentheses. X plus 6y plus 6y minus 9x equals 4. And the second one is 2x plus y plus 4y minus 6x equals 3. Now, this is the system we need to solve. Let us continue simplifying. What we have, putting all the terms together, is a system of negative 8x plus 12y equals 4, and the second one is negative 4x plus 5y equals 3. And now this is our system, and if we want to solve it, we can use any method. If we want to use elimination, we should multiply the second one by 2, by rather negative 2, to get a cancellation of the x terms. So now we have negative 8x plus 12y equals 4. In the second equation, we're going to multiply by negative 2, giving us 8x minus 10y equals negative 6. And this is our system now, and what we get is a nice cancellation of the x variable. And then we add the y's, and we get 2y, and then we add the constants, and we get negative 2. Giving us y equals negative 1. That is one entry of our 3 tuple. And now we figure out the others. We figure out the x by choosing any equation with an x in it. So negative 4x plus 5, y equals 3, but we know y is now negative 1. So this becomes negative 4x minus 5 equals 3. So minus 4x equals 8. X equals negative 2. This is another entry in our 3 tuple. And now we can use the third equation we had for z. Z is 2y minus 3x. Y is negative 1. X is negative 2. So z becomes negative plus 6, which is 4. So z equals 4 is the third entry in our 3 tuple, giving us a final solution of -2, -1, and 4. This is the 3 tuple that solves the system. This was solved a little differently than the previous one, but the principle is still the same. We went from a system of 3 equations to 3 unknowns to a system of 2 equations and 2 unknowns. Once we solved for one of the variables, we started plugging in into appropriate equations to get the values of our 3 tuple. And for the last problem in this video, we will do an application problem of where you might run into a system of 3 variables and 3 unknowns. I'll just write down the system and the solution. I won't solve it. So this is the problem. We have 500 tickets sold. We know that the adult price is $7.50. The child price is $4, and for a senior citizen ticket, the price was $3.50. And we also know that the total revenue was $3,025. And we need another piece of information. We're told that twice as many adult tickets were sold as child tickets. And the question is, how many of each type of ticket were sold? In the last video, we had an application problem with just adult price and child price, but with a system of 3 variables, we have an application of 3 different prices, 3 different amounts. So first, we label things any way we want it. X, let X be the number of adult tickets. Let Y be the number of child tickets. And Z be the number of senior tickets. And now we're going to use the first equation, the first information, that there were 500 tickets sold, to write down the first equation. Well, this means that the total number of tickets was 500, so X plus Y plus Z is 500. The second bit of information, we're told that all the prices of the tickets and what the total revenue was. So our second equation is going to set money equal to money, 7.5x plus 4y plus 3.5z equals to 3,025. Finally, the third piece of information, how many adult tickets were sold with respect to child tickets. And we need this third sentence because we cannot solve 3 equations, for 3 unknowns with just 2 equations. We need a third equation. This third equation is the number of adult tickets is twice the amount of child tickets. So this is the system, and solving the system will solve the problem. Now I won't do this. I won't solve it here. You can solve it in the same manner as we solved the previous problems. But the basics is that you take advantage of the simplest equation here, which is x equals 2y, and you substitute that into the first and second equation, and then what you end up is an equation of only y's and z's. And when you do that, the final solution becomes x is 300, there are 300 adult tickets, there are 150 child tickets, and there will be 50 senior citizen tickets. So that is just one example of how you can apply a system of 3 equations in 3 unknowns.